Okay, so in this class we are going to start integral calculus. So that is you have to define what is a double integral, triple integral. Okay. So same thing we already discussed about functions of single variable and then Riemann integrable. Okay. So there how we define the integral of your function. Suppose f is a function defined on some closed interval a comma b. Okay, so f should be bounded function. Suppose some closed interval a comma b to r be any function, and we define we take some partition here. Okay, so we take some partition capital P is set of finite number of points x0, x1, etc. xn, and we define there are two sum. So before that we define what is capital Mi is the supremum of the function in the interval xi and xi minus 1. So that is set of all f of x where x varies in the interval xi minus 1 comma xi. In this interval the maximum value of the function we denote capital Mi. Small mi is infimum of the function in the interval. So infimum of the function in the interval xi minus 1 comma xi, the ith interval. And then using these mi's we define upper sum, lower sum with respect to this partition. So we denote UPF. Upper sum we define summation mi into the distance we define delta xi. Okay, so delta xi is nothing but the length of the interval, ith interval, that is xi minus xi minus 1. That is delta xi, where I equal to 1 to n. So similarly, we define the lower sum is summation small mi into delta xi, where I equal to 1 to n. So you'll get upper sum, lower sum. So if you increase the number of points in the partition, the upper sum reduces and then the lower sum is increases. Okay, so if you increase the number of points in the interval in the partition, the upper sum is reduced. So therefore for each partition we can define we can find the upper sum, right? So therefore upper sum of these we are going to take the infimum of this collection, but P is a partition. For all partition P is a partition. For each partition, you have to find the upper sum and then take the infimum partition of this closed interval a comma b. Okay, we call this is a lower. Sorry, this is called the upper limit. So that is upper integral a to b bar f of x dx. So similarly, for each partition, you have to find the lower sum and then take the supremum of lower sum of the function, where here partition is varying. That P is a partition. So you are varying all the partition and then take the supremum. We call this a lower integral denoted by a bar b f of x dx. Okay. Now, if both exist and both are equal, then we say it's integral, and then we define the common values integral a to b f of x dx is nothing but the common value integral a bar b f of x dx and equal to integral a b bar f of x dx. So in the single variable, we call this is actually area of the function bounded by the curve f of x and x equal to a, x equal to b, and y equal to 0. Because we draw the graph for this one. So suppose we have a plane. So in this we have 2 points AB because the domain is AB. So if we take A is here, B is here. So the function is continuous function, should be continuous. So therefore maybe the function like this. So therefore for each point we can define the function. Now we can look at this as a like this shape. Okay, so this is B. Now the area of this region we denote integral a to b f of x dx. So it's bounded by the curve. So this is x equal to a line. Okay. And here this is x equal to b line. And this line is x-axis y equal to 0 line. And this is f of x, y equal to f of x. So area, so this is nothing but area bounded by area of the region. Okay. Area of the region bounded by x equal to a line and x equal to b line and y equal to 0 line and y equal to f of x. Okay. So we need a 4 function, we get a region. So therefore area of this region we call, okay, the shared region. We can take this shared region. So the shared region we call is a area. So this is only for single variable. The function is a single variable and the function is bounded function. Then we can find this, we can talk about the integration. Okay. Now similarly we can extend function of single variable into function of 2 variable. In that case, we have to find the volume of the region. Or if you go to the 3-dimensional, we can say volume. Okay, for 2-dimensional we can say area. If you go 3-dimensional, we say volume. So now suppose we give the function of 2 variable. Okay, so here we call, if this is satisfied, then we say this f is Riemann integrable. Okay, so if the limit exists, both are exist and equal, then we say f is a Riemann integrable or just integrable. Riemann integrable on the interval, closed interval a comma b. Okay. Now we can, similar idea, we have to extend this definition to the function of 2 variable. Okay. Suppose f of x comma y is a function of 2 variable. Suppose f of x comma y is a continuous function. That is very important, because without continuous it's very difficult to find that area. Okay, so f of x comma y is a continuous function. That is very important condition, should be continuous. Okay. Continuous function defined on some bounded region. Okay. So that is f is a function from some d to r or r to. So continuous function defined over or defined on a bounded region. Because if the region is unbounded, we cannot find the area or volume of anything. So it should be bounded. Bounded region in the xy plane. So that is, if you take some region, bounded region, we call R. Okay. So R is some any bounded region in R2, bounded some region. Boundary region of on the plane R2. Now f is defined on this capital R, not R2. Okay, so don't confuse this R and this one. So we can, if otherwise call some other name. Suppose D. D is some boundary region. F is defined on D to R. Be continuous and should be continuous function. Okay. Now we have to define maybe if you look at the picture, what is this actually? So if you look at the thing, it's very difficult to look at, but anyway, the graph should be in the 3-dimensional. Okay. So in the 2-dimensional case, so here we choose our domain is x-axis. If you take the closed interval a comma b in the x-axis, and then we can, for each point we can we have a graph. So similarly, but here the domain is xy plane. So maybe this is some x and this is some y somewhere can take. So maybe this is y plane and this is z plane. Suppose D is somewhere. So this is our set domain D. So for each point in the domain, we have a function, and then we have to find that area bounded by area, the region bounded by the function f, and then this base point is this region D. Okay, so same thing. Again, we have to take. So we know that how to find the area of a rectangle or anything. So you got to find some rectangle covered this D. So you can find a suitable rectangle. Okay, cover this D. Okay, and then now we can take partition for this one. Again, here take partition of this one. If you draw the lines again against this, you'll get small rectangles for each partition. If you draw this, you'll get small region. Okay, now look at this. Maybe I can pick one region. Suppose I pick this region. Okay, so this is some rectangle. So what is the area of this rectangle? Is nothing but this length and this length. So maybe this length is delta x, x-axis length is delta x, and this length is maybe delta y. Maybe we can call. So maybe we can call this small region is we call some name AI. So the corresponding is delta xi, delta yi is nothing but area of this particular rectangle or portion. So similarly, we can find for each rectangle, we can find the area. So, but if I look at this portion, maybe I can write some other color. So again, we can find, we can easily find the area of this one, area of this one. So after that, you got to sum all the things. But if you look at this portion, this is not rectangle. Okay, this will look like some triangle or something. Okay, so how to find this type of this area? So again, so if you split more than this, okay, so if you consider more points on x-axis, more points on the y-axis, so you'll get very small rectangles. So then you can easily. So same thing here. We discussed in the first single functions of single variable. We increase the number of points in the partition. So similarly here. So but here there are two cases, x-axis and y-axis. So here maybe look like the partition there, but Cartesian product of two partition. One partition on the x-axis, another partition on the y-axis. If you increase more number of points on the both the partition, you can cover more area in this region. So same thing, and then you got to sum all the things. Okay, so same thing what we discussed in the function of single variable. So here we increase the number of points in the partition, you'll cover more area. But here function of two variable, therefore we have a two side, x-axis and then y-axis. Therefore both the partition you have to increase the number of points. Therefore we can cover more area. Okay, so therefore the length between any 2 points in the partition, if you take one partition, one point here xi, xi minus 1, and another point is xi. So the distance between these 2 points are very small. Then we can cover more area. Okay, so that's I am going to state now. Okay, so first we define simple case and then we go to the general case. Okay, first we define what is the double integral over the rectangle. Okay, first we start with the simple diagram D. The domain is simple diagram, and then we can go for any arbitrary D like this one. So first we start with the simple domain rectangle. So the first one is double integral over rectangles. That is, domain is if we take rectangle, and then if we take continuous function, what is the area or what is the volume? So double integral over rectangles. So actually, how the rectangles look like this. So in the xy plane, the rectangles look like this one. Okay. So therefore, maybe this is we call A and this is B. Okay. Otherwise, so in the xy plane, so rectangles may be like this somewhere. This is our domain D. So therefore, for corresponding point here, I call A, and corresponding point this is B. So here we call this C and this is D. So we call rectangle, we call R. Okay, R is the rectangle. Suppose our domain is R. Suppose the function defined from R to, okay, don't confuse with this R. This is not a real number, just a notation for a region, okay, or rectangles to R. But R, this capital R is a subset of R2. So actually simply saying this R is nothing but the Cartesian product of the two interval A comma B cross close interval C comma D. Okay. So this is nothing but Cartesian product of these two interval, you will get this rectangle. So therefore, if you take, if a function is defined f of x equal x comma y equal to some number, some output is it. Now, what is the range of x? So x varies from the first set, y varies from the second set. Okay, so therefore the definition of R is nothing but collection of all ordered per x comma y such that a less than or equal to x less than or equal to b, and then c less than or equal to y less than or equal to d. So this is a rectangle. So the function defined on this rectangle. Okay, now what is the volume of this bounded by this one? So for each point, in the point, if you take some point here, some xi comma yi. So this point maps to somewhere. Okay, anyway, so for any, if you take any points here, it maps to somewhere. So therefore, you'll get some region, okay, bounded by bounded below by this bottom, bounded above by the curve f. Okay, but it's very difficult to visualize the graph. But base point is this one, and then you will build a so you have to for each value you'll get something. You get some graph like this. So is some region bounded below by R, bounded above by this curve f. So it's very difficult to find entire there. Therefore, you have to split the small region and then you can find it. So if you, again, you have to, okay, maybe I erase all the things. Okay, now we have to split small regions. You have to take some partition on the x-axis. You can take partition on the y-axis. You'll get same thing. So if you look at this region, so maybe this look like some graph like this. Okay, so only that piece. Maybe we'll get some rectangle like this. Okay, so you can easily find the area of this one. So again, you can find, look at this portion, and this maybe look like this. Okay, actually not this one. Maybe some graph like this. So you have to find the area of each rectangle, and then you have to sum. Okay, maybe I can write the formal definition. So maybe we can call, if pick some area here. Suppose I pick this portion is A or A1 or something. Suppose I take generally A. So you can take anything, A1, A2. You can call the name of this interval, name of the portion. What is the area? So what is the delta A? Is nothing but area with only for this region. Suppose I call this delta x and this length is delta y. So the area is nothing but delta x into delta y. Suppose otherwise we call this is 1, A1, then what is the area of A1 is nothing but delta x1 into delta y1. So this is notation. Okay. So there are so many small rectangles in the region. We can call A1, A2, etc., AN, and so on. The corresponding areas we denote delta A1, delta A2, etc., delta A. So we have so many rectangles. We call the rectangles A1, rectangle regions. So we call some name. These are all area of this particular A1, A2, etc., and so on, A3, and so on. So these are all areas. Area of A1, A2, etc., respectively. Okay. So if this is A1, then the area of this one is delta A1. So suppose this is A2, then area of this is delta A2, and so on. Okay. Now you pick some point in the AI. So suppose I pick some point. Suppose this is AI. I pick some point here, xi comma yi. Okay, and then we can find the value of that one. So we call that is Sn. Suppose in the region Si contains maybe delta An. There are n regions A1, A2, etc. An. So delta A1, delta A2, etc. delta An are the area of this respectively this one. So we define the sum Sn. So similarly, so already we define for the single variable, we define upper sum, lower sum. So similarly, we define something here. So this is nothing but summation. If you fix some point xi comma yi in ai and then find the value of the function f of xi into delta of ai, where I equal to 1 to n. Okay. So in the rectangle, maybe I can one more time I will draw the graph. So we have a rectangle R. So we split into small regions. We found there are so many rectangles. Suppose I found one rectangle. We call this is AI rectangle. Okay, and area of this rectangle is delta AI. Suppose I pick one point here. Suppose I pick one point. That point is called xi comma yi. Okay. Now the image of the point xi comma yi, and then I have to multiply with this, because this is height. Okay, so if you look at only this piece, if for all points of these, if you look at this, maybe the graph is bounded by maybe this one. Okay, only if you look at any point in this AI, the function is defined. Therefore, for this point, maybe this we will get, and for this point, maybe we will get the ranges here. For this point, maybe we'll get some range here. So you connect all the things. It's a continuous function, right? Because the function is continuous. We will get only we can get this point. Now, what is the height? So therefore, you can pick some point, and then maybe this is f of xi comma yi. This is the maximum height, maximum. Okay, but it's not exactly. Maybe the graph maybe look like this. This is not a rectangle, but if you find some point, we can choose some arbitrary point and then take the f of xi. Consider this maybe lower sum or something. Okay, so you'll get this side. So what is this side? F of xi, and then what is the area of this bottom? Delta a. So take this region. Again, if you take some other some aj, okay. So for each point, we can have a function. Therefore, the graph may be look like this one. Again, what the height I can choose. If you choose some point x2 or xj comma yj, you get a f of xj comma yj. This is the height. Therefore, base is delta aj. Height is f of xj comma yj. So therefore, you can find the area. So for each rectangle, small rectangles, we can find this sum. But this is not exact area. Okay, so you can get exact area when we'll get exactly. Okay, maybe so we define Sn equal to summation I equal to 1 to n f of xi comma yj, where this xi comma yi, this point is in ai. Okay, if I equal to 1 means x1 comma y1 belongs to a1, x2 comma y2 belongs to a2, and so. Okay, now if you take okay, so this delta xi and then delta yi goes to 0. So this actually delta x length, this is delta y length. Suppose this length are very close and this length are very close. Maybe this rectangle very small rectangles, and maybe you will get in the height is also maybe you can get some straight line. Okay, so what we did in the first function of single variable. So if we increase the number of points, suppose if you take very small points, okay, maybe I can take here. Suppose if you look at this point, look at this point and B, you will not get a rectangle because maybe you can get this rectangle. So this area is missing. Okay, suppose you are choosing very close to one point. Maybe I can choose some point here. So if you look at this rectangle, maybe you can cover this portion. So suppose if you take one more point here, you will get some point here, but in the original one we get this region. Suppose I choose this point also, we get cover now this portion. So if we increase the number of points, otherwise simply saying the distance between any two points in the partition is very small, we can cover more area. Okay, so now this area is missing. Okay, which area is missing? Maybe I can. So now this area is missing. So suppose I am choosing one more point middle in between here. So therefore, you can draw the line here. Now you can draw some rectangle. Now some of the portion is covered. Anyway, this portion is missing again. So again, I can choose one more point between these two. I can draw the line. Maybe you can get some rectangle. I can cover this portion also. Okay. So if you choose more points or the base bottom length is very small, then you can cover maximum area. That's the same thing here. But here there are two sides, delta x and then delta y. If delta x and delta y is approaches to 0, so what is actually delta ai is nothing but delta xi, delta yi. This is base and height for this only that portion. Okay, we need a small region. Therefore, this approaches to 0 means what? This length, this x-axis length, this is delta xi. This approach very small length, then we cover more area. Similarly, for if in the y-axis side also, you can reduce the size, length of the size, then we can cover more area. So that means what? If delta x and delta y is approaches 0, we cover more area. So now we define. It is called actually. So here delta is increasing, right? Now what I am going to take. Now I am choosing here. There are n region. The partition actually this is actually partition. In this case, this is a partition. So here the partition contains n portion a1, a2, etc. an. Suppose I am increasing the number of portion, we can cover more area. So that means what? I am going to take the number of points. Therefore, limit n goes to infinity Sn. Okay, I am going to take more number of a region. So it's same as what is the same? We have to reduce the size. So actually, this is nothing but simply saying limit delta ai goes to 0. Summation I equal to 1 to n xi comma yi into delta a. Okay. So this is called, we denote double integral over the region R, the function f of x comma y dx dy. Okay. Or simply we can write. So I hope everyone understands what is the, how the definition is defined. Okay. So similar to the single function of single variable. Okay. Anyway, so how we define this one? We define the notion integral, double integral over R, rectangle. Okay, f of x comma y into dA. So dA is nothing but that area of the region. Or we can simply use some other notation in double integral over the region R, rectangle, function of xy into dx dy. But here we know the range of x. So x range is from A to B, y varies from C to D, because we assume that it's a rectangle. So therefore, we define, in general case, we define in double integral over R, f of x comma y dA is nothing but limit delta A is approaches 0. Delta A approaches 0, summation I equal to 1 to n f of xi comma yi into delta ai. Okay. This, what is this a, and then what is the meaning of this ai is nothing but actually delta, generally speaking, okay, delta a goes to 0. That is the same as delta I goes to 0, but I am simply saying delta a goes to 0. If you reduce the length of the domains, that is delta x side and then as well as y side, you'll get small rectangle. Therefore, you'll get so many rectangles inside this region. Therefore, it covers maximum area. So we call that area is maximum volume. Okay, we call this double integral over R f of x dx. This is for general case, but if you know x is bounded by a and b, integral a to b, integral c to d, f of x comma y dx dy. Maybe I state the properties of this integral. Suppose we have two function. So next, the properties of double integral. Properties of double integral. So over the rectangle. Now the base is rectangle. So the first property, suppose we have a constant double integral over the region k times f of x comma y dx dy, or simply we can say dA is nothing but you can take k outside. Double integral over R f of x comma y dA for any k. Okay, for any k this is true. And second, if you sum or subtract two function, that is double integral over R f of x comma y plus or minus g of x comma y dA or dx dy. You can write anything is equal to double integral over R f of x comma y dA plus double integral over R f of x g of x comma y dA. Some okay, plus or minus. If you take plus or minus, then also plus or minus. Now the third one is, suppose this f of x is positive. Suppose if f of x comma y is greater than or equal to 0 in the entire region R, then the double integral also positive. Double integral over R f of x comma y dA is greater than or equal to 0. It's also positive. That is the third property. Now the fourth property is that, suppose we have a two function f and g, satisfying them, f of x comma y is bigger than or equal to g of x comma y on the entire region R, then the double integral also bigger than this one. So double integral over R f of x comma y dA is greater than or equal to double integral over R g of x comma y dA. The fourth property. Now suppose this R rectangle we can split into two partition. Okay, suppose this is a rectangle. Suppose this R can be union of two portions. This is another portion R1. This is another portion R2. Suppose this R can be written as disjoint union of R1, R2. Then double integral over R, simply write double integral over R1 plus double integral of R2. If R1 equal to R1 union R2, but R1 intersection R2 is disjoint. Okay, that is the next property. Suppose double integral over R f of x comma y dA can be written as sum of two things. So double integral over R1 f of x comma y dA plus double integral over R2 f of x comma y dA, where R is nothing but R1 union R2, but there is no common element between R1 and R2. That is R1 intersection and R2 should be empty set. Okay. Now we define this actually volume. If n goes to infinity, so we define now what is volume. Volume is nothing but this limit. So volume equal to is nothing but limit n goes to infinity. This Sn. Already we defined what is Sn. Okay, Sn is summation f of xi comma y delta a. So that is we define volume. Okay. Now we have some theorem calculating the double integrals. That is called Fibonacci theorem for calculating. So actually, suppose R is bounded, then double integral over R f of x comma y dA, simply we can write a to b integral c to d f of x comma y. Since this limit is for y, therefore you got first you got to write dy and then you got to write dx. So dy dx. Okay. If you know the bounds of the region, you can simply write this limit on this interval. Okay. This is the meaning of the double integral. Now we have a theorem. So the theorem called Fubini's theorem for calculating integrals. Calculating double integrals. Suppose we have a function f of x comma y, or simply call some z. Okay, suppose we have a function f of x comma y equal to 4 minus x minus y. But the function is defined on the rectangle R. What is the rectangle actually? Set of all x comma y such that x varies from 0 to 2 and then y varies from 0 to 1. Now we have to calculate this one. So therefore, we simply write volume or that is volume. It's nothing but double integral over R f of x comma y dx dy. So this is nothing but maybe you can write x values 0 to 2 and then y range is 0 to 1. F of x comma y is nothing but 4 minus x minus y into dy. Don't write dx because the first integral is the range is y ranges. Therefore, you have to write dy into dx. So this is equal to, first you have to evaluate the inside integration. If you integrate this with respect to y, we get 4y minus, treat x is a constant. Therefore, xy minus y square by 2. If you integrate with respect to y, substitute the upper limit and the lower limit into dx. If substitute the upper limit, lower limit, what will get? So this is equal to integral 0 to 2. If substitute 1, we get 4 minus x minus 1 by 2. If you substitute 0, all the term contains 0, therefore 0. Okay. We get this one into dx. Now, if you integrate this with respect to x, we get 4x minus x square by 2 minus x by 2, 0 to 2. So, substitute the upper limit, we get 8 minus 4 minus 2 is 2 minus 1. If substitute 0, we get 0. Therefore, 5. So, 5 is the volume of that region bounded below by this rectangle, bounded above by the function f of x comma y. Okay. Maybe roughly I draw the graph of this picture of this one, how this look like. Suppose we have a R3. Okay, sorry. Okay, R3. So this is maybe I can take this is x-axis and this is y-axis and this is z-axis. So here the rectangle is 0, x range is 0 to 2. Suppose this is 0, this is 2, and y range is 0 to 1. Suppose this is 1. So you will get a rectangle like this, the bottom. Okay, so therefore the bottom is the rectangle. This is the domain. Okay, now for each point we define the function is okay. Now, so what is the function? Maybe I call z. Okay, z is 4 minus x minus y. Now look at this corner point 0, 0. You substitute x equal to 0, y equal to 0, you get 4. Therefore, on the z, you will get, actually this is 0, 0, 4. The maximum we'll get this one. So again, for each, now I we evaluate at the point. Now you can evaluate by this point, evaluate this point, evaluate this point. For each point you can evaluate. So similarly, each point you can evaluate. So you will get the region like this. Maybe so maximum. What is the value of this one? Maybe is go somewhere. So if substitute z equal to 2. So what about this point? Actually, this point is everything is 0 except x coordinate. Therefore, 2, 0, 0 is this point. If substitute here x equal to 2, sorry, okay, yeah. Not actually this is on the x-axis, right? Okay. So if substitute here, what you'll get? Z equal to 2. You'll get Z equal to 2. So therefore, maybe this is Z equal to 2. Corresponding here, maybe you get this value. So maybe you can look at this. So again, for this point, if you look this point, actually this is nothing but 2, 1. Okay, so x is 2, y is 1. If substitute here, what is the Z value? 1. So maybe somewhere, maybe here 1. But you have to visualize the thing. Okay, so again for this point, what is this? X is 0, y is 1. Therefore, we get 3. So maybe 3 is somewhere, is maps to this. So for the corresponding and this point we can get. So similarly for this one you will get this. But this is not a cube, okay? So the heights are different. So here height is 2, here height is 4, here height is 3, here height is 1. Okay, keep in mind this is not a cube, but it's a some shape. Okay, so volume of this portion is 5. Okay. Any doubt in this? You can interchange the limit also. So first you can integrate x, substitute the x range, and then you have to do for y. Okay, anything you can do. Either first and second, this one. So now I state what is Fibonacci theorem, first form, and then we can go for stronger form, Fibonacci stronger form. So first theorem, the theorem is called Fibonacci theorem. Fibonacci or Fibonacci theorem. But this is a first. This is first form. What the theorem says, suppose we have a continuous function f of x comma y. So if f of x comma y is continuous on the rectangular region R, on the rectangular region R. This R is the range of x is a less than or equal to x less than or equal to b, and then c less than or equal to y less than or equal to d. So this is a rectangle. Then the integral over R, double integral over R, f of x comma y dA is nothing but integral c to d, integral a to b, f of x comma y dx dy. Because first we have a limit of x. Or this is same as first you take a to b and then c to d, f of x comma y dy dx. So this is Fibonacci first theorem, as the Fibonacci theorem for first form. Okay. If you know bounded thing, so maybe quickly we solve one problem related to this, and then we move to the next form. So example, calculate double integral over R f of x comma y dA for the function f of x comma y equal to 1 minus 6x square y. And the region R is x ranges from 0 to 2, and then y varies from minus 1 to 1. Okay. So by Fibonacci's theorem, integral of the over double integral over R f of x comma y dA is nothing but, you can take anything first. Suppose I take 0 to 2 and then minus 1 to 1. What is f of x comma y? 1 minus 6x square y dy dx. So first you have to integrate with respect to y. Therefore keep this and then treat x is a constant. Keep fixed. Therefore integration of 1 is y minus 6x square y square by 2. Therefore 3x square y square into dx. Oh, sorry, you have to substitute upper limit, lower limit, minus 1 and then plus 1. So what you'll get? So if you substitute upper limit is equal to integral 0 to 2 1 minus 3x square minus, if substitute minus 1, we get minus 1 plus minus 3x square thing into dx. Now if you simplify this is equal to integral 0 to 2 1 minus 3x square minus minus plus 1 minus minus plus 3x square dx. So 3x square cancel, we have 2. If we integrate, we get 2x. 0 to 2. Therefore, we get just 4. Okay. So 4 is the volume of this region. Okay. So now, so far we discussed double integral over rectangles. Suppose the domain is not rectangle for any other region, non-rectangle, same thing will happen. Okay, that's it. You have to split into small region, and then you have to apply the limit, the delta A goes to 0, you will get the exact region. So same thing. Okay, that is not thing. Or now we can go for the next theorem, Fibonacci's theorem for stronger form. Okay. So Fibonacci's theorem for stronger form for double integral over non-rectangular region. For rectangular region, we know that both x and y are bounded by some constant, that is rectangle. Non-rectangle is what? Maybe once one variable is bounded by some number, but the other variable depends on the one variable, other variable. Maybe this y depends on x or x depends on y. So that is next thing. So how to integrate that type of integration? So that is a theorem. That is Fibonacci theorem. Not Fibonacci, sorry, Fibonacci's theorem. But this is a stronger form. Stronger form of this theorem. So what is the theorem says? Suppose again we have a continuous function defined on some region R, but region need not be rectangle, maybe any region D. So if f of x comma y be continuous, on a region R, so first says, suppose if R is defined by, the region is defined by, suppose A is bounded by, sorry, X is bounded by A and B, but G is bounded by some function of X, G1 less than or equal to Y less than or equal to some G2 of X. This Y bounds are depends on x. Okay, where this g1, g2 are continuous function. Okay, where this g1 and g2 are continuous on the closed interval a comma, because x ranges over a to b, right? Therefore, this g1, g2 are continuous on the interval a comma b. Then what is the integration? What is the volume? Then double integral over r f of x comma y dx dy, or it's simply say dA, is nothing but integral a to b integral g1 of x into g2 of x. So first you have to cancel the integration where the limits are variables. Okay. So here x is a variable. So because the y coordinates have a variable, therefore first you have to evaluate the first integral and then evaluate the constant limits. So that is the first point. Suppose g is bounded but x is depends on y, then you have to evaluate x first and then evaluate y. So that is second. Okay, so if r is defined by so now the y is fixed, that is y is bound by c and d, but the x bounds are some function of h1y less than or equal to x less than or equal to some h2y, where this h1 h2 are continuous h1 and h2 are continuous function on c comma d, continuous on, because it's defined on y defines on c to d. Then what is the double integral? Now double integral over r f of x comma y dA is nothing but first you have to evaluate x, that is h1y to h2y f of x comma y dx into dy. Okay, so that's it. Maybe we discuss some example to this one. So therefore Fibonacci theorem, the first form is both the limits are constant, both the bounds for a and b, for limits of x and the limits of y are constant, then that is the Leibniz first form. The stronger form is one of the limits should be depends on other variable. Now we discuss some example. Find the volume of the person whose base is, okay, anyway they I write the full thing, you can understand what is the region. Okay, find the region or find the volume. Find the volume of the prism whose base is the triangle, whose base is the triangle in the xy plane bounded by the x-axis and the line y equal to x and the line y equal to x and x equal to 1, and whose top lies in the plane z equal to f of x comma y. There is f of x comma y is nothing but 3 minus x minus y. That's it. Now it is given that the region is triangle. So first you have to try to draw the triangle and then find the range. So it's given that triangle is bounded one side, because triangle we have a 3 side, right? So one side they given that x-axis. Okay, therefore is x-axis is one thing. Now another one is x equal to 1. So this is a 1. So x equal to 1 is one line, and then another one is given that x-axis. Now another one is given that y equal to x line. Therefore, if you draw y equal to x line, you will get this one. So what is the common portion? This is a triangle. So this is a common portion. Okay, so this is our rectangle. Sorry, this is our region R. Therefore, what is the range between x and so now look at this. So x ranges from 0 to 1. Okay, so but this y ranges from 0 to x. Okay, so therefore this y depends on x. Therefore, now we'll get range of x is 0 to 1. But what is the range of this? This y start from, because this is y equal to x line. So therefore, maximum x, minimum 0. So it's depending upon x. Okay. Now this is now what is the volume? W integral over R f of x comma y dA. The volume is nothing but, first you take the constant limit and then take the variable limit. But what is the function? 3 minus x minus y dy dx equal to integral 0 to 1. First you can integrate this with respect to y. We get 3y minus xy minus y square by 2, 0 to x into dx. Now this is equal to integral 0 to 1. If substitute x, we get 3x minus x square minus x square by 2. If substitute 0, all the terms contain 0, therefore 0. Okay, into dx. Anyway, this is actually 3 by 2 x square. Otherwise, anyway, finally you can simplify. Directly integrate, you get 3x square by 2 minus x cube by 3 minus x power 3 by 6, 0 to 1. So if substitute 1, we get 3 by 2 minus 1 by 3 minus 1 by 6 minus 0. Okay, so what is the value? You'll get 1. So you can take 6 is a LCM. So you get 9 minus 2 minus 1. So therefore 6 by 6 you'll get 1. So therefore the volume bounded by this triangle and then the function, the volume is 1. Okay. Any doubt in this? So anyway, we can change the thing also. Okay. Anyway, so maybe we'll discuss one more problem and then we can stop. Otherwise, I give exercise, you try to calculate. So double integral over R sin x by x d, where this R is a triangle whose bounded by x-axis. Okay, again the line y equal to x and then x equal to 1. The same thing. Therefore, what is the region? So what is the volume? So simply we can write this is equal to integral x range is 0 to 1, y range is 0 to x, sin x by x dy dx. Since sin x by we got to treat as a constant, therefore integral 0 to 1 integration of dy is y. Therefore sin x by x we get just y, but 0 to x into dx. So if substitute the x cancel, we get a sin x. What is the sin x of the integration is cos x minus cos x 0 to 1. Therefore this is equal to minus cos 1 minus plus cos 0. So therefore, what you'll get? This cos 0 is 1. Therefore, this is equal to minus cos 1 plus 1 is approximately maybe 0.46. Okay. But we can reverse the order. Suppose we can change, because we know that 0 less than or equal to x less than or equal to 1, and 0 less than or equal to y less than or equal to x. Okay. Now this x is less than or equal to 1. Got it? Now we have a bound for y. Now we get a new, we can interchange the reverse order. Now we get a x, y varies from 0 to 1. So therefore, what is x? So therefore, x varies from 0 to y. Oh, sorry. Because the minimum value for x is y, right? So therefore, minimum y, maximum 1. Now look at this one. X range, x bound for y to 1. Therefore, now we can reverse the order of integration and attempt to try this one. So therefore, we get integral 0 to 1. This is a y limit. So x limit is y to 1. Sin x by x dx dy. Okay. Now it's very difficult to integrate this sin x by this one, right? So maybe we can. Okay, so we have stopped the fact that this integration, the inside integration, one that is integration of sin x by x dx cannot be expressed in terms of elementary function, sin x, x square or anything. So there is no general rule for proceeding, which is order of integration will be good. Okay, so maybe we'll discuss the next class how to be interchange the order, raise change of variable. Okay, maybe I can stop now.